right, everyone. Good noon. Let me go ahead and... All right. Good noon. This is our last lecture of new material. I'm seeing here my videos a little... Okay, just checking to make sure the video is actually running decently. Last lecture of new material, so after today we will have covered everything in the entirety of the class. The next 2 days are just going to be review days, where I'm just going to go through and kind of like the review days did before, just kind of covering very quickly all the equations we've covered thus far. So I'll probably be mainly using those PowerPoints where I already made the equations and stuff like that. And what I'll go through is kind of highlight some of the key ones where I've seen maybe areas of particular challenge, and then provide maybe a few example problems in areas where I've seen particular challenges. But that'll be the next 2 days, and there's no clicker questions for any of those, so those will just be for your own benefit. So you're welcome to join me for those and ask any questions during the stream itself, or you can ask questions outside of that. But yeah, if you show up during it, during the live stream, any questions you may have, you're welcome to ask, and I'll try to answer them during that time as well. As far as the final is concerned, I need to update it on here. But the plan is to offer the final, so it seems like there's no restrictions on when it can be done. So I'm going to keep it on the same day because I don't know what your other classes are doing, and so I want to make certain that I am not conflicting with other classes or any plans that you may have already had for these things, or making it so that you have to do 2 exams at once. So the plan is, it's Administrative Professionals Day next Wednesday. Isn't that exciting? So the exam's going to be on the 22nd as it was originally scheduled, and I have to double check when exactly we had it scheduled, but I will again offer that 12-hour time span to take the exam. Let me get out of here so we don't see myself talking to myself. Just like the last test, I'll give you 12 hours to take the test during. My current plan is to probably do the exact same structure we had for test 2, where I give you a bunch of multiple choice questions. My current plan is to do 30 questions, though that number could shift. If it does, I'll let you know. So 30 multiple choice questions. And regardless of how many questions there is, I'm going to do the same thing I did for test 2, which is allow you to make up 10% of the points. So if there's 30 questions, that'll mean you can turn in 3 questions you got wrong with your worked out solutions. So pretty much exact same structure as test 2, which I imagine will go pretty well based on how test 2 went for most people. It's going to be cumulative, so it's going to have everything on it that we've covered in the entire class. As far as the amount of content from each section, so if you go ahead and go to, well, this is mostly accurate. Each week of content is going to basically have an equivalent amount of information in it. So that's one way of thinking about it. Or each, so for instance, we're covering optics. So that's electromagnetic waves. We're covering that right now. And so that's going to have just as much content on the test as, for instance, DC circuits or electric potential. Just because we're covering these later doesn't mean they're going to have more on the test. They'll have the same amount as everything else. But you won't have seen this information on previous tests. And a better way to probably think about it is the quizzes. The topics covered in each quiz are going to have equivalent ratings, because we did collapse a couple items because some of them are kind of small. Specifically, we collapsed DC circuits and current together, and we collapsed AC circuits and inductors together. So, no. So Jacob asked, would the makeup questions be due on the same day? No, I would give you. The current plan is 2 days to do those as well. So I can't give a super long time because I need to start doing grades. But 2 days I believe will be more than sufficient time. So same thing as last time. I provided the exam on Wednesday, and you had to have your worked out solutions by Friday at midnight. So the same thing will be there. And I'll have this all in writing. I'll send this all to you in writing after this class. the worked out solutions will need to be submitted by the Friday the 24th at midnight. Okay, so that's the current structure for it. And that's what I'm going to run with for now. If anything kind of comes up, anything changes, I'll certainly let you all know. One thing I am trying to do right now as well is I'm trying to get, there's the physics I care about number 2, so those are almost all graded. I just have about 40 of those left. You can see that here. I have 43 left of those to grade, so most of you all should have the grades for that. The rest of you will have it by the end of today. I am also trying to get all the lab grades, so you all have gotten emails saying that the lowest grade you will get in the labs is the grade you had before spring break. So everything after spring break will only increase your lab grade. And so I'm trying to get the lab grades from TAs for the scores before spring break. Once I have those, I've sent out the emails. I got it from some instructors, still waiting on some of the TAs. Once I have those, I will upload all of that. And the reason for that is, I believe by the 20th, so let's go ahead and pull this up. By the 20th, you need to have made the decision on whether you are going to have your grade be a letter grade, so A, B, C, D, F, or whether you're going to have it be satisfactory or unsatisfactory. And so I want to give you as much information as possible to make an educated decision there. I sent out an email previously kind of outlining what my recommendations are. Basically, if you have an A or a B in the class, I would probably stick with the letter grade. If you have a C, satisfactory is probably going to be better. But other than that, you'll have everything. Once I get those lab scores in there, that'll be everything basically that we've done so far. That will include everything, except maybe I think the last quiz, which I'll also try to fix. So that's all the logistics done. We are going to go ahead and move into the very last section of content and get this completed. And this is on thin lenses. So it's kind of interesting here. This thin lenses kind of stuff is a bit more borderline between physics and engineering, because we're not actually exploring, we're not doing all the derivations to kind of get to the point of figuring out how these work. But there is some physics, because basically we're just missing a little bit of details, and I'm not going to go into the derivations for it because it's just too it's not necessary in this case, and it's a bit too complicated. But basically the idea is you have light coming from air, and it's going to hit a thin piece of some transparent material. Pretty much it's always glass, but it could be literally anything that's transparent. And these lenses are designed such that if you have something called a converging lens you can see here has kind of these rounded outsides to it on both sides. A converging lens will take all light that is coming in, if the light is coming in parallel, and it will cause the light to converge on the focal point. So these lenses are designed very specifically, they're shaped very specifically so that they have a focal point at some specific spot, and all the light that's coming in parallel like this will hit that focal point. Note, if you have light kind of going up like this, that does not go to the focal point. The light rays have to be coming in parallel, completely flat like this, intersecting this kind of vertical plane perpendicular. So that's the and this is called a convex or a converging lens. They're both the same thing. These are just two names for the same thing. And I'm going to tell you the quick way of remembering convex from concave, because concave is the second one. Concave has these divots. So this is called a concave or a diverging lens. So instead of it kind of being bowed outward, it's bowed inward. And the idea here is that light, which is going in parallel, will end up getting kind of spread out, will end up getting dispersed. But if we took these rays and we imagine that they actually came from some source in a straight line, all of them intersect with the focal point, instead of being on the right side, on the left side. So these dotted lines are not reflections. These dotted lines are imagining that this line was a straight line from a source, as if there wasn't a piece of glass here and these lines were coming from some point source. Because they're coming from a point source, this light travels in a straight line. The way we remember concave versus convex is these are divoted in, which is kind of like a cave. Caves are going to be dug out areas into a hill or something. And then convex is the other one. That's how I remember it. That's kind of just, remember cave, caved in, convex, bowed out. And future case, you're ever uncertain, you can just Google it. And then diverging or converging is pretty straightforward. These converge, the actual light rays do. They diverge, they separate. Okay. And these have different functional applications. You will use these in combination with each other for actual real-world applications, or maybe you'll just use one. It all depends on what you're trying to do. You can clearly see if you were trying to focus light at some point, you would use a converging lens. And we'll see a diverging lens is actually very beneficial if you want to make something look larger. So, for instance, a magnifying glass. Ironically, you may think a magnifying glass may end up using this, but actually, if you want to make something bigger, you're going to use a diverging lens. Okay, so the next thing we're going to quickly cover, this is called ray tracing, and ray tracing, it's going to seem like a lot of information, but they're just rules. These are just rules to follow, and I'll go ahead and show the next picture because I think the visual is easier to kind of digest at first instead of seeing a massive wall of text. The purpose of ray tracing is that it allows us to see, so if we have some object on one side, imagine your eyeball's on the right, and you're looking through this lens to see another object. Well, your eyeball is going to interpret it based on this image. So the image is what's actually, as the light goes through, it's going to get bent in certain ways and make this image, and that's what your eye is going to kind of see. And so this ray tracing helps us to see what the lens is actually doing. And you see here that the convex lens versus the concave lens have different rays going in different directions. And there's basically 3 rules here. You see, so we're just going to focus on one at a time. So let's just focus on convex. There's 3 rules to follow to determine how light goes from the object and how, when it hits the lens, how it ends up bending. And they're literally just rules that you follow. Don't need to understand too much about it. Don't need to do all the math behind how this bends. And this is where the engineering kind of comes in, and where we don't really get to the physics is, why does it bend this specific way? Well, that's due to how the geometry is designed and index of refraction. So we're not going to worry about it though. We're just going to worry about how do we draw these. So let's look at line 1. So line 1 is already one that we kind of talked about, pretty straightforward. If you have a parallel line, so a line going kind of flat along, this is called the optical axis. Optical axis just passes straight through the lens. So the lens is standing up and down. Optical axis passes from on left to right. So it's exactly perpendicular to the plane of the lens. So if you have a ray of light that's going parallel, it's going to hit the lens, and it's going to go at an angle such that it passes exactly through the focal point. So we already saw that. That's exactly what this shows here. Any parallel ray follows this, and the same thing here. Any parallel ray follows this, passes through the focal point. So that's pretty straightforward. The second ray, and you'll notice here we're taking the lines and we're starting at the top of the arrow. I could have picked any point on this arrow. This arrow is just like a made-up object, a teddy bear, a tree, who cares what it is. The idea here is that at every point on this object, it's emitting light, and that light is going in all sorts of directions. But if we can figure out how a few of those rays converge into a single point, it turns out, this is kind of interesting, if I picked any ray, let me just pick this random ray here, it would also converge at this point. But we picked these 3 because they have these really nice, easy rules to follow. But the consequence of this is that literally every single ray, so this, at the top of this object, it's emitting rays in every single direction. Every single one of these rays that hits this lens will end up passing through this exact spot. Why? Because if 2 or more of them do, then they all do. That's the idea behind a converging lens. Okay. So we got our first one. That's the easiest one because that's the one we already covered. The second one is also very easy. It's literally you draw a line going from the object, and you draw it straight through the center of the lens, and it just keeps going straight. So if you pass a ray of light if you have a ray of light that's going directly through the center of the lens, it doesn't get deflected at all. It keeps going straight. Okay? And at this point, honestly, these two rays are sufficient to draw the picture. Once you see, I say draw the picture, once these converge, that's where you get this image. This image is if you like put a screen here. If we put some kind of screen here, the light, and we could, so say this was a tree, we'd end up getting that tree looking upside down right here. Okay, so if we put a screen here, let's call this a screen. And I'm going to write image over here because I kind of overlapped it. This is what the light would end up getting displayed on. And it would be a very clear picture because all of the light rays are getting focused. If we move the screen, and you would actually see this if you did the labs, unfortunately, you can't do the in-person labs because you can't go in person with each other. You would see that if you move the screen to the left or to the right, you would still see this image, but it would be blurry. So it's only when the screen is exactly here, you're going to see a very crisp image because all the light rays go together. It's going to be fuzzy because at this point, you can see here, the top of the arrow here, the light from it is in 3 different points. And so you get kind of this fuzziness of the arrow. In this case, it's an arrow. Okay, so that's light ray number 2. Light ray number 3 is if you have a light ray that intersects the mirror. So you go, well, it's actually easier just to do this. Where these two intersect, you draw a straight line, and that line going back is going to give you light ray number 3. So that one you kind of have to already know where the image is on some level. And all of these are written right here. So you can see here a ray, this is rule number 1. A ray entering and converging, and these are broken down into converging and diverging, so just focus on the first sentence. A ray entering a converging lens parallel to the optical axis passes through the focal point on the other side of the lens. So parallel passes through the focal point. A ray passing through the center of a diverging or converging lens keeps going straight. Keeps going straight. And the last one, and this is, I missed this when I was first describing it. For 3, a ray of light that is passing through the focal point on the left side. So it has to pass through the focal point. You see here we go exactly through the focal point on the left side. When it hits that, it's going to make a parallel line on the other side. Which makes sense because that's symmetry. If we look at these sides, this is, number 3 is the opposite of number 1. Okay. So you can see that here, a ray that passes through the focal point exits the lens parallel to the optical axis. And you can see here I already denoted that these are opposites of each other. Okay, so I'm going to give you all a couple minutes to digest this converging lens. Feel free to kind of read through the diverging one. So you'll need to have these slides open to kind of go back and forth, unfortunately. I'm going to just leave the visual open for the next couple minutes. But we'll reconvene at 11:51. And I'll answer any questions in the meantime, but just kind of look through this. We talked about this first one. When we come back, we're going to talk about the second one, and then we'll talk about some final equations and do a practice problem. Oh, and I have to somehow not make this interfere with this. Alright, well, hopefully you have the slides open on your computer, because if I make this bigger to show Buster, then unfortunately that covers up that thing. But there he is. Oh, somewhere. That him? I can't tell. Yeah, he's just apathetic to everything. Brandon was asking, is Friday our last lecture? No, we're going to have a lecture on Monday as well. Classes end on the 20th. That's why that Deadline is the 20th for the satisfactory, unsatisfactory, or grade thing. So Monday is our last lecture. We're taking 2 days to do the review because we have a whole semester's worth of content to go through. Okay. So there we go. So we covered the 3 rules of this, of how a converging lens works. We're going to go ahead and continue on with the lecture and get the rest of this finished. One thing I want to highlight before we even move to the diverging lens. The reason we're talking about screens and about how this will portray on a screen versus how it looks in your eyeball is because if you look at this with your eyeball, well, your eyeball is actually a lens. So if you looked at this light that's coming off this thing with your eye, your light will actually see something different than if you see it broadcast on a screen and then onto your eye. Because once it's onto the screen, it's effectively like there's an object here. It's going to look like that object is here on the screen in this fashion. So if the actual object is upright like this, imagine, again, what you would actually see in a lab. Let me draw this. If you're doing this experiment in the lab, and I think it's good the way they do it, is what they do is they take a piece of metal and there's a cutout of that arrow. And what they do is they then put a flashlight, so some light bulb behind it. And that light bulb emits light through the thing, through this arrow. That light passing through the arrow is going to be in the shape of an arrow. It then passes through the lens. And so you then put a screen here. And what you end up seeing is you see the arrow upside down on the screen. You see, you see a lit up arrow on that side. So everything else is dark, and then there's light that in the form of an arrow. And so when your eye sees this, so this light hits here, and then once it hits the screen, that light's going everywhere. And so your eyeball is over here, and your eyeball sees this light, and it looks like the thing because that's what it is. On the screen, there's a lit up arrow. Your eye sees that arrow. If you were to see it, so if the screen was not there and your eye saw it, these light rays, instead of acting like a normal image here, they're actually going all over the place. And so your eye's lens then does something different with them and makes them look even different. So if you, for instance, looked through this thing with your eyeball, your eye's going to act as another lens and is going to do something to it. So that's why we put the screen there. Okay, so that's that. Okay. So if we talk about the diverging lens, this one has different rules, exception of rule number 2. Rule number 2 stays exactly the same. If it passes through the center, it keeps going. That's the easiest one to remember. You draw a line from any point on the object. I could draw a line from the middle of the object. If it passes through the center, it continues on through the center. Rule number 1 is instead, so let's look at rule number 1 for the converging because we're going to kind of compare these two. Instead of it going, so it's going parallel, still going parallel. And instead of passing through the focal point on the right side, it diverges. But if we imagine that diverging line was a straight line coming from some source, it'd be at the focal point. You draw it, and then you draw this dotted line kind of back. This is not a reflecting ray. This is kind of just a fake ray that we draw. That's just a straight line from where it actually goes. So the light goes, it bends upwards, and we kind of go backwards in a straight line. This is how we figure out how much this one goes upwards. Or if it was on the bottom, goes downwards. Rule number 3 is we draw a line from the top of the object all the way through to the focal point on the right side. So remember, on this side, we intersected the focal point. For a converging lens, we intersected the focal point on the left side. For a diverging lens, we intersect the focal point on the right side. And this line hits the lens, not a mirror. And the way we then draw the line is wherever it intersects. So we draw that line all the way from there. This dotted line is not actually where the light goes. We just use that as a guide, because once we draw that line, the intersection with the lens tells us, okay, we draw a straight line, and that's the way light actually goes. So let's just go ahead and draw. I'm just going to go ahead. I'm going to erase this because this is from last semester. And I'll go ahead and go through those 3 rules because I think it's easier to see me draw it than it is for me to talk about it. So let's draw just a random shape. In fact, let's pick something different. We're going to pick a Christmas tree just to demonstrate. There it is. It's beautiful. Just to demonstrate what this actually means, instead of showing an arrow, show something that looks more real world. We make our diverging lens. We say it has some focal point. We say that I somehow drew this thing actually correctly. Let's draw our optical axis of this thing. So the optical axis passes through the center. So I need to draw my object. You have to be very careful how you draw these things. If you draw them incorrectly, when you're tracing these lines, you get the wrong image. We'll say the focal point is here. The focal point is symmetrical on both sides. So both sides have a focal point that are the same distance. Okay. And we have this thing flat on here, so let's go ahead and go through the rules. Rule number 1, we take our line. It goes straight, it hits here. We then draw that dotted line to the focal point, and that tells us that our light goes in that same direction as that dotted line to the focal point. So that's rule number 1. Okay, let's do rule number 2. Rule number 2, we'll call that one green, is we pass through the center, and that's it. You pass through the center. It's a little curved, but imagine it wasn't curved. So there you go, passing right through the center. Rule number 3, we take our thing and we go from here to the focal point on the other side. And actually I messed this up because what I want to do is I want to go to here and then I want to draw dotted lines because these are not the actual lines. And this intersection here, once it intersects, it then goes straight. So that's it. That's the idea. And you can see here I did a bad job of drawing it because ideally all 3 of these things would intersect. Maybe if I had drawn this thing a little bit straighter. But the idea here is now that my Christmas tree, this is where the image is roughly located. Again, ideally, if I had drawn this actually correctly, you can see here my dotted line should be a little bit higher, which would make the green line a little bit higher. In fact, I am going to just imagine that these end up going through correctly because I don't want to confuse you all when you go back and like, why does this look terrible? Well, it still looks terrible. Ideally, I would be using a ruler for this. It's very hard to do this on my screen with a ruler. But it's close enough. The intersection of all 3 of these points, we'll just say it's this. You can see that more clearly in this picture. The intersection between the green line. Oh, and that's why. Oops, I made the mistake there. It would have been way better looking if I had done it correctly. The way we get the intersection is we actually take the dotted line from the red one. And actually, they do all intersect. So we got pretty close. That's the intersection of all 3 of them. Not this awful thing up here. All right, let me just refer to the better looking pictures so you can see it. So we drew line 1, goes parallel, goes up. We draw that dotted line back. We draw line 2, goes straight through the center. Great. We draw line 3. It passes through the focal point. We draw that dotted line on the right. We draw a straight line here. And then we draw a dotted line backwards and a straight line as if this light, because the idea here is we are tracing all of these lines on the right and straight lines. So this one, the red one, we go in a straight line backwards. The purple one, we go in a straight line backwards. And the green one, we go in a straight line backwards. Because the idea here, it's as if there is an object. Imagine the lens wasn't here. You would generate these same lines if there was an actual object located here. That's basically everything that this is saying. You can see here, it's as if this one is making lines outward as if there was an actual thing there. The diverging lens makes line outwards as if there's an actual object here. Instead, it's on the left side. And this is what a lens does. Your eye is going to interpret these lines as if there is something here. In the case of the first one, your eye is going to interpret these lines as if there was something actually on the right side, when in reality it's on the left side. Oh, there's a ruler tool in the draw tab. There is, but when I say a ruler, I meant like I would hold it against the screen and use it to actually draw straight lines. These are not the straightest of lines because I'm freehanding it. So just as far as keeping my lines actually following a straight path. So that's what I meant when I said ruler, but I appreciate that, Alex, that recommendation. So all this to say, lenses bend light to make an object look like it's actually somewhere else, and they can flip this, they can make it look like it's upside down, and they can increase or decrease the size of it. So this has all sorts of applications. So say if you want to look at an object, maybe you want to make the object look larger than it is. And the way you would do that, remember I said this is actually what a magnifying glass will use? That's because when you put an object in between this focal point and the lens, it actually makes an image that's larger. So here it made a smaller one, but if you actually put this object over here, it'd make a bigger one. So that's one application. Another one, clearly if you wanted to focus light to a point, you would use a converging lens. And so this one still can, depending on how you move it around, could still potentially do that. But, okay. So that's all the imagery for it. I'm not going to ask you all to do these ray tracing diagrams. I still want to talk about them just so you've seen them. Some of you may end up seeing them later down the road, and so this is a very important tool to determine how these lenses actually operate and the result of them as light passes through them. And we needed to talk about this idea of the object and the image. The object is the actual literal physical thing, and then the image is what it actually, when you look through it, it's like, oh, it makes it look like the object is actually over here. This is the image. It's a fake thing. That is the, if this lens was not here, this image would act the same way that this object's light does once it passes through that. So it's kind of a fake thing. And this is, again, beneficial because you can imagine if you want to look at something, if you want to look at it bigger, well, you can't literally make your object bigger, but you can make the light bend in such a way that it's as if it came from a bigger object. So something to just think about some more. All that to say, this is the math behind it. This is how you would actually solve a problem, and this is something I will ask you to do, where basically we have our object, the distance from the object. So let me go ahead and draw a fake lens here so I can just draw all these different variables and where they would appear. So here's our object. This is the distance to the object. It's the distance from the lens to the object. The focal point, F, is the distance from the lens to the focal point. And then the distance for the image, remember for this specific problem, the image was on the right side. It could be on the left side depending on the problem. This is our image. And this is our distance to the image. Distance from the lens to the image. So you can see that's all I'm writing there, but now there's a picture to match with that. One thing to keep in mind that's very important, distance to the image can be negative. A negative, so this is a positive image distance because it is on the opposite side of the lens as the object. So the object is on the left, image is on the right. So this is a positive DI, this is a positive DO. Let's go ahead and draw the opposite example, which is the diverging lens. We had our object here and it made an image over here. Again, the image locations can change. So image, object. This is a negative image distance. So, and I'm going to go ahead and just draw something to separate these so we don't mix them up together when you're looking through these notes. This is a negative image distance. Why? Because they're on the same side. Okay, so when you're doing these problems, you have to know whether it's positive. You have to know whether it's on the same side or the opposite side. Again, for all the problems I'm going to give you, I will tell you this detail. I'll tell you if it's on the same side. I'll tell you it's on the opposite side. Or I'll tell you that it's negative or positive. So it's going to be very explicit. And problems outside of this class, if you saw this in maybe other more advanced classes, or if we had more time, you would actually have to draw the image diagram. You would have to do the ray tracing. So maybe it gives you the object distance and it gives you the focal point and it gives you what type of lens it is. You would actually have to do the ray tracing, see where the image is. And once you saw where the image is, you would determine if it's positive or negative, if it's on the same side or the opposite side. Pretty much a good rule of thumb you can see here is that the object and the image are going to be, well, in the case of the one we did here, we only did the ones where the object is to the left of the focal point and the image object here is the left of the focal point. Basically, there's a whole table of rules that you can even follow where you don't even need to actually draw it. But again, we're not going to spend the time on that. Last one, the focal distance, and this is very important. This is one I won't tell you whether it's, I won't say, oh, f is -5 or f is +5. I will tell you if you have a converging lens or a diverging lens. If you have a converging lens, f is positive. That's just a rule. If you have a diverging lens, f is negative. That's just a rule. So, pretty straightforward. You literally just plug in the value. So just like follow these rules when you're doing the problems to make certain you have the right numbers. And these will give you, this is just a really simple relationship to kind of see where things will end up. Here's the problem. So here's a very simple problem. I gave you a convex lens, which is a converging lens. And so you just need to find the location of the image. I gave you the image of the object. I gave you the focal distance, convert into meters, and then solve the problem. Okay. Last thing is magnification. Magnification is literally just how big is the object, or sorry, how big is the image compared to how big is the object. So let's go ahead, and I know we're running out of time. I'm going to try to finish things up in the next 3 minutes. I kind of went over my usual time, so I apologize for that. But I want to just get everything done and make certain everything's as clear as possible. Let's go ahead and look at this one. Actually, this one's easier to see. You see here my image is about 1/4 the size of this. So your magnification is how tall this thing is divided by how tall this is. So this is, maybe we'll call this 4 meters high. This is 1 meter high. Your magnification is 1/4, which makes sense. Your lens has made the object appear 1/4 it's made it 1/4 the size of it. It now looks 1/4 smaller if you looked at it. If you use this lens in this exact setup. This also has a very nice relationship where it equals the negative of the distance of the image over distance of the object. And one thing that's important to note here, it's negative. So if HI, so your magnification, if that gives you a negative value, that means that your object is, let's go ahead and look at this one. This is a positive because they're both upwards. So my thing hasn't flipped. Whereas here, it's going to be negative because it flipped upside down. So if you looked at it, you would see it's upside down. And so that's a negative magnification because so if you actually plug these in, it's upside down. So we call the height of the image as a negative value. We'll just say positive if upright. Negative if upside down. So that's an easy way. And both of these follow these rules, HI and HO. So if the object is upright, and you can define what upright is, it's positive. If it's negative, if it's upside down. If you define the arrows being upside down when it's pointed up, well, that's fine. They'll end up canceling each other out as long as you're consistent. Okay. Eddie quickly asked, does ray tracing explain how prescription glasses work? Yep, that's exact. prescription glasses. Now those are more complicated of a shape. They're not necessarily convex or concave. The glasses that you use kind of have this curve to them, but they'll maybe be a bit thicker on one side and thinner on the tops and bottoms, so they will act like a lens. So they're not quite, you can't quite use as simple rules. It's a little bit more complex, but they do the same thing. They bend the light such that it changes where the focal point is, because ideally you want the focal point for your eyes. When light comes in, you want light to focus so that it hits the back of your eye. That's where you want the focal point to be. As your eyes get, so I can kind of draw this. So here's your eyeball, light's coming in, and here's the back of your eyeball. So this is the front of your eyeball. There's your wonderful eyebrows. You want the light to focus. So if we somehow drew straight lines here, you want the light to focus at the back of your eyeball, because that's where your receptors are. When you have any kind of near vision or far vision, that means your lens is not able to move that focal point exactly right. And so maybe if you have one of them, I don't know which one's which, so I'm not going to try to say. But if your focal point's kind of back here, you get a fuzzy image because now the light is not intersecting at one point. It's intersecting at a bunch of different points. And so that's bad. And if you have the focal point before, same thing, light's going to kind of bend outwards and you get a fuzzy image. Okay. I am going to quickly solve through this. If you want to stick around, you can. I'm just going to do this because I don't mind spending a few minutes, but I apologize because I've gone over. But just so you all can actually see how I do a calculation, I want to complete this and be done since this is the last thing. So we have a convex lens. And I'm just going to do part A. Should take a few seconds. So part A, we have our convex lens. And we have to find the location, orientation, and magnification of an image for a 3 centimeter high object, which has a focal length. This is our focal length, and this is 10 centimeters, which is 0.1 meters. And our first place is 50 centimeters, so our object is going to be way over here. So that's DO equals 50 centimeters equals 0.5 meters. And this thing has, and let's go ahead and draw our optical axis for. There's our optical axis, and it's 3 centimeters high. This is totally not to scale. I drew it bigger, but it just makes my life easier to draw. 0.03 meters. I'm not going to worry about ray tracing here. Okay. So find the location of it. So we need to find, so part A, DI. Well, we're going to use 1 over DO plus 1 over DI equals 1 over F. Now we already know for this problem that because this is very similar to the example I gave before, that this is going to make some image over here. It's the object, it's to the left of the focal point, it's a convex lens, it's going to make an image that's upside down over here. So, that means opposite sides, DI is positive. In fact, this is the nice thing, because I gave you DO and I gave you F, you would end up finding this anyway. So, if we're solving for DI, it's going to be 1 over DI equals 1 over F minus 1 over DO. So DI equals 1 over 0.1 minus 1 over 0.5. To get DI by itself, I have to divide this all by 1. So you plug in all those values, and I find my calculator. 1 divided by 0.1 minus 1 divided by 0.5. And you get DI equals 0.125 meters. Look, we got a positive value. Look, it matched what we expected it to be. When you're doing this math, if you know what the values of DO, if you know the values of 2 of them, plug them in, and it's going to tell you whether the other one is, and it'll tell you whether it's positive or negative naturally. You don't need to make that change yourself. The equation will tell you it for you if you know 2 out of the 3. All right, so orientation, I mean, it's upside down. So upside down. Done. And what's the magnification? Magnification equals negative di over do equals 0.125 divided by, so negative 0.125 divided by 0.5, and that's going to give you 1/4. Sorry, negative 1/4. So look at that. That's how easy these problems are. That's how easy I'm making them for you all. I'm not having you do anything fancy. Literally, it's just going to be a lot of plugging and chugging. I'm pretty much going to give you the values of their positive or negative. And again, we don't have time to go into these in detail. Otherwise, I'd do a bit more. Okay, so that is everything. We're at the end of the slides. We got through the equations. We got through the ray tracing. We got through optics. So thank you so much, everyone. I hope... Again, we're going to do the review days. It's not the end of everything. But please spend the next, before the test, go through the problem sets. Please come to my office hours if you have questions on anything. I have office hours today at 1. Whatever you need, please just make certain you're working on this material. And again, ultimately, I want this class to have been beneficial for you. That's why you're taking it. While it's maybe required for your major, that's generally because it should be helpful for you. So I hope that you found some stuff in here that has been interesting and that you can see yourself using in the future. If not content-wise, I hope you've developed some kind of critical thinking skills to be able to look at a problem, be like, oh, here's a bunch of information, and then being able to use a set of tools to process that information to get what you want to get out of it. That's physics in a nutshell. Is all we're doing is you look at the world, you get a bunch of information, you come up with tools and equations to be able to understand them and predict and explain things. All right, have a great rest of the day, everyone. If I see you at office hours, I'll see you then. Hopefully see you on Friday and Monday for review stuff. And it has been a pleasure. Again, not the end, but it's as far as the end of content, so I feel like there needs to be some kind of conclusion statement there. All right, goodbye, everyone, and thank you for the kind words.